Pluto made them come all along. It was like it was never actually a section of the nearby planet group's planetary progressive system. Pluto's circle crosses that of another planet, and that is no sort of conduct for a planet. Pluto, the baffling smaller person planet at the edge of our planetary group, is creating a ruckus in the galactic local area. Late reports suggest an approaching crash with Neptune, igniting worries among researchers and space lovers alike. Prestigious specialists, including Neil deGrasse Tyson and Michio Kaku, have raised cautions about the potential results of this celestial conflict. However, how precisely did Pluto find itself on a crash course with its far-off neighbor? And what could this grandiose crash mean for our world on Earth? Join us as we dig into the startling situation developing between Pluto and Neptune. Pluto, once viewed as an undeniable planet, was later renamed as a dwarf planet due to its remarkable orbit. Nonetheless, this change does not stop it from continuing to spellbind and draw in the cosmic community. Later forecasts from unmistakable researchers, including Neil deGrasse Tyson and Michio Kaku, have highlighted an unsettling closeness between Pluto's trajectory and that of Neptune. These specialists are forewarning about a potential impact between the two planets, representing a critical danger to Earth. The peculiarity of Pluto's venture around the Sun lies in its unique qualities within our nearby planetary group. Its orbit spans in broad 248.8 years, and since its discovery in 1930, Pluto has not completed a full revolution. What adds to its interest is the exceptionally elliptical nature of its orbit, a departure from the nearly circular orbits of the major planets. Moreover, Pluto's orbit is marked by a 17 degrees tilt to the ecliptic plane, making its path steeper in contrast to other planets. This mix of tilt and centricity presents layers of complexity to Pluto's orbital pattern. A remarkable part of Pluto's orbit lies in its crossing point with Neptune's path. For roughly 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their respective positions in the solar system. This prompts the question, why hasn't an impact between Pluto and Neptune happened? The explanation lies in the gravitational influences exerted by other planets. The assessment of Pluto's orbit began shortly after its discovery, presenting an astonishing direction for cosmologists. In contrast to most planets, whose orbits align relatively close to the ecliptic plane, Pluto's unique features include a steep tilt and an elliptical shape. The mystery expanded with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricacies inherent in space mechanics. The three-body problem in space involves understanding the motion and gravitational interactions among three celestial bodies like Pluto, Neptune, and the Sun. It is akin to predicting their paths based on initial positions and mutual gravitational influences. For Pluto's situation, this problem explains the intricate interplay between its orbit, Neptune's orbit, and the gravitational pull of the Sun. Terms like asymmetric libration, scope libration, and the VZK oscillation contribute to unraveling this celestial riddle. Astrophysicists state that AOL libration, responsible for maintaining planets in their orbits, plays a crucial role when it comes to Pluto and Neptune. This term means that when Pluto crosses Neptune's orbit, it is situated no less than 90 degrees away from Neptune, vitally preventing potential crashes. Scope libration, referring to the upward movement of a celestial body in its orbit, ensures that when Pluto approaches Neptune or other giant planets, it is positioned significantly above their orbital plane, providing an extra layer of protection against impacts. A key factor in understanding celestial motion is the VZK oscillation, named after three researchers von Ziepel, Lilly, and Kai, who studied the gravitational interactions between three space objects like Pluto, Neptune, and the Sun. The VZK oscillation explains why Pluto's orbit around the Sun appears erratic but remains stable over time. Despite the apparent randomness in space, underlying patterns and rules maintain order. These factors generally stabilize Pluto's orbit, preventing crashes with Neptune or deviations from its path. The three-body problem helps us understand how the gravitational forces of these space objects influence their paths. Studying this adds to our knowledge of Pluto, our solar system, and distant celestial bodies. Mathematical simulations in the late 1980s revealed that despite its chaotic properties, Pluto's orbit is actually stable, with minor initial deviations leading to significant differences over millions of years. Nonetheless, Pluto's exceptional orbit maintains stability over incredibly long timescales, keeping chaos at bay. Recent computer simulations have enhanced our understanding of how large planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun-Neptune special resonance, where it completes 3 orbits for every 2 of Pluto, contributes to stability. Jupiter's gravity also plays a significant role, and Saturn has a smaller effect. Together, these forces ensure Pluto's safe and stable movement through space for billions of years. These phenomena are crucial for maintaining order and consistency in the motions of objects in the universe. Without these components, the solar system would be a place of greater chaos and unpredictability, potentially leading to crashes or ejections from stable orbits affecting other celestial bodies. Understanding Pluto's orbit is vital, especially in discussions about a potential impact with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of our solar system. Pluto's case highlights how seemingly unstable orbits can reach harmony through the intricate interplay of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our position in the universe. Exploring the depths of space often reveals the erratic nature of celestial bodies, and Pluto's orbit serves as a prime example of this unpredictability. The concept of orbital disorder, illustrating the delicate reliance of a celestial body's path on its initial conditions, is vividly demonstrated in Pluto's case. Even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Programmatic simulations have been instrumental in helping researchers understand how Pluto moves in space. These simulations use complex numerical models to replicate the gravitational interactions between Pluto and other celestial bodies like Neptune. By making small changes in the simulations, space experts can observe how minor alterations can have a major impact on Pluto's trajectory. In the late 1980s, these simulations uncovered an intriguing aspect of Pluto's orbit. Despite features like AIML and scope libration that contribute to its stability, Pluto's orbit can still show unpredictability. Even a small initial difference in Pluto's position or speed can lead to significant changes in its path over many years. Despite this inherent chaos, Pluto's orbit remains stable for an unusually long time frame, extending over billions of years. This suggests that beneath its seemingly erratic appearance, Pluto's journey around the Sun follows an organized order. Predicting the long-term behavior of celestial bodies, especially those with eccentric orbits like Pluto, is extremely challenging. The inherent unpredictability of these systems makes long-term predictions uncertain. Mathematical simulations help us understand and anticipate the future paths of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily rely on precise initial conditions and replicate complex interactions. Even a small error can lead to dramatically different outcomes, making accurate predictions difficult. The turbulent nature of celestial orbits, such as Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how each planet's presence and position can influence the stability and trajectory of other bodies within the system. Despite these complex forces, prominent astrophysicists are now expressing concerns about a possible collision between Pluto and Neptune. This raises questions about why such a crash, which seems unlikely given these unpredictable factors, is now a subject of concern. Neil deGrasse Tyson, a notable astrophysicist known for making astronomy popular, offers a unique perspective on the mysteries of our solar system, especially with regard to Pluto. Famous for renaming Pluto as a dwarf planet rather than a true planet, Tyson shares insightful thoughts on how our understanding of celestial mechanics is continually evolving. Tyson views Pluto's renaming not as a downgrade, but as a necessary adjustment in line with our growing understanding of the various objects orbiting the Sun. His approach to celestial mechanics involves ongoing learning and adaptation. He sees the complexity of orbits like Pluto's as an indication of how much more there is to discover in space. Tyson believes the allure of these questions is what makes astronomy so fascinating. Furthermore, Tyson is aware of how space-related events and discoveries shape public interest in astronomy. He believes that events like Pluto's renaming and its unusual orbit present opportunities to captivate the public's imagination and curiosity about the universe. By discussing the dynamic and sometimes irrational aspects of space mechanics, he opens a window for the general public to marvel at the wonders and mysteries of the cosmos. Working alongside other researchers, Tyson is actively warning the public about the potential risk of Pluto's unpredictable orbit. After studying Pluto extensively, he has raised concerns that the three-body problem could pose a real danger, suggesting that a collision with Neptune is long overdue. Furthermore, he emphasizes that such a collision could disrupt the balance of the universe and lead to catastrophic consequences extending to Earth. A collision between Pluto and Neptune would be an extraordinary and devastating event in our solar system. This crash would release a massive amount of energy, potentially breaking Pluto apart due to its smaller size and icy composition. Debris from the impact could scatter across the solar system, posing potential risks to other planets and their moons. For Neptune, such an impact might even alter its environment and orbit, depending on the specifics of the crash. Michio Kaku, a renowned theoretical physicist known for his work in string theory and science advocacy, offers a fresh perspective on the issue. He warns that the unpredictable paths of celestial bodies like Pluto and Neptune underscore the delicate and complex forces at play in space. Kaku suggests that even the slightest changes in the gravitational forces affecting Pluto and Neptune could lead to unforeseen and potentially catastrophic consequences for the solar system. He believes that studying these celestial bodies offers important insights into the dynamic and unstable nature of the cosmos, which will help us in future space exploration. While a Pluto-Neptune crash is unlikely in the short term, scientists agree that long-term monitoring of these celestial bodies is essential. The work of scientists like Tyson and Kaku brings attention to the need for more observation and research on the forces influencing Pluto's erratic orbit. Monitoring these planets could help identify any signs of danger and allow for preventative measures should an impact occur in the far-off future. As scientists continue to monitor Pluto's orbit and its relationship with Neptune, the potential for a future collision remains a topic of ongoing research. While current simulations suggest that the likelihood of an impact in the immediate future is low, the dynamic nature of celestial bodies means that changes in orbital mechanics could always occur, making long-term predictions challenging. One of the key challenges for astronomers is the sheer scale of time involved. While Pluto's orbit is stable over the course of its revolution around the Sun, nearly 250 years, this doesn't guarantee stability on shorter timescales. The three-body problem, which governs the gravitational interaction between Pluto, Neptune, and the Sun, is incredibly complex, with multiple variables that influence the stability of their orbits. As researchers continue to refine their models and simulate different scenarios, it becomes clear that even a small change in one body's position or velocity could potentially trigger a series of events that leads to a collision, albeit in a timescale much longer than human lifespans. In addition to the gravitational interactions between Pluto and Neptune, the role of other large planets, like Jupiter and Saturn, cannot be ignored. These massive planets exert significant influence on the entire solar system, and their positions and movements could alter the path of smaller bodies, including Pluto. For example, Jupiter's strong gravitational field is known to affect the orbits of many objects in the Kuiper Belt, where Pluto resides. Any shift in Jupiter's position could potentially alter the balance of forces that keep Pluto's orbit stable. For this reason, planetary scientists are placing a renewed emphasis on observational programs that track Pluto and other distant objects. Telescopes and space missions dedicated to the study of the outer solar system, such as NASA's New Horizons mission, provide valuable data on the movement of dwarf planets and other objects in the Kuiper Belt. These observations are crucial for updating orbital models and ensuring that any changes in Pluto's orbit are detected early. Despite the dramatic and unsettling nature of the possibility of a collision, it is important to note that, for now, there is no immediate threat to Earth or any other planets in the solar system. The dynamics between Pluto and Neptune remain stable in the present day, and while future changes may occur, these would likely unfold on timescales far beyond the reach of current human civilization. Still, the discussions brought forth by prominent astrophysicists like Neil deGrasse Tyson and Michio Kaku raise important questions about the nature of celestial mechanics and the unpredictability of space. While the possibility of Pluto colliding with Neptune seems remote, it underscores the vast complexity of the cosmos and the importance of continued research in understanding our place within it. Tyson, Kaku, and other experts advocate for a deeper engagement with the mysteries of the universe, suggesting that every new discovery can help unravel the fundamental laws of physics that govern everything from the smallest particles to the largest galaxies. In the end, whether or not Pluto will ever collide with Neptune is still a mystery that will require further observation and study. However, the intrigue surrounding this potential collision is just one example of how our understanding of space is continually evolving. As technology advances and our ability to observe the far reaches of the solar system improves, we will likely uncover even more secrets about the celestial objects that inhabit it, allowing us to better predict their behaviors and perhaps even prevent future cosmic disasters. For now, Pluto remains a fascinating and enigmatic part of our solar system. Its eccentric orbit and its complex relationship with Neptune serve as a reminder of the wonders and challenges that await in the study of the cosmos.